Hello Chem 1B, this is our solution chapter, video 5, and we're going to be talking about gas solubility. Now in this case specifically, we're talking about how soluble a gas is in a liquid. So this has a lot of applications. If you've ever wondered, like fish need oxygen still to survive. They don't breathe it, they use their gills to siphon it out of water. And what this means, and what you may not realize, is there's oxygen gas dissolved in water that the fish's gills allow it to kind of filter out. Now, there are other applications of this. If you've ever had a soda or a carbonated beverage, there is dissolved CO2 in that soda. Now, right now we're going to talk about how temperature affects the solubility of a gas in a liquid. And gas solubility almost always decreases as temperature increases. So you can kind of see this graph here. This is our concentration on the y-axis in millimolar, so just molarity, but millimolar. And as you can see, as we increase temperature on the x-axis, the amount of gas that can be dissolved at that temperature is decreasing. This is true for almost all gases. An easy application that you may have had happen to yourself of this is if you've ever left like a soda out. Usually we drink soda cold. This is because there is more CO2 able to dissolve in the soda when it's cold. And so as the soda heats up, that CO2 that was dissolved in it gets released. It comes out of the beverage. And then if you leave your soda in your car, it gets really hot, you're going to get a flat soda. It's going to taste like syrup because all the CO2 has left the beverage.
All right, so continuing with that trend, the other effect on a gas dissolving in a liquid is the pressure of the gas itself. So the higher your pressure of your gas above the liquid, the higher the concentration of that gas dissolved in the liquid. So if you've ever opened a soda, almost always you hear that as the gas escapes from the soda. And that's because they put a high pressure of CO2 above the soda to keep a really high concentration of CO2 in the beverage. Now, we have an equation for that, which is called Henry's law. Henry's law gives you the concentration in molarity of your gas in a liquid if you know Henry's law constant and the partial pressure of the gas. So this isn't the total pressure. That's really important. It's the partial pressure. So let's do a problem like this. So again, solubility, Henry's law constant, and partial pressure of our gas. I forgot that I had those there. All right. So let's say, hey, we want to calculate the amount of dissolved oxygen in water at the following temperatures when the container is in a room with an atmospheric pressure of 1 atm and a mole fraction of oxygen in the air being 0.21. We know our Henry's law constant at 5 degrees Celsius and 40 degrees Celsius are these two values. And we have our equation as Sg is equal to Kh times our partial pressure of oxygen in this case. So we can erase these lowercase g's and put O2 because that's the gas we're trying to calculate for. So we need to calculate the partial pressure of oxygen, and we know partial pressure is equal to the mole fraction times the total pressure. This is from chapter 5. Now our partial pressure of O2 then is times the mole fraction, 0.21, times 1 atm of pressure, which gives me a partial pressure of 0.21 atmospheres. This guy goes there. And we have our Henry's law constant. So at, for instance, 5 degrees Celsius, then we would have SO2 is equal to 1.92 millimolar, that's just the milli prefix, per ATM, times 0.21 ATMs. ATMs are going to cancel. We're going to be left with our concentration here. And we get that the concentration should be around 0.403 millimolar of O2 dissolved in the water. At 40 degrees Celsius, this isn't much different. We do the same thing, right? 40 degrees Celsius, SgSO2 is basically equal to 1.01 millimolar per ATM times 0.21 atmospheres. Atmospheres cancel. We're going to be left with about half of the dissolved oxygen present of what we had at the 5 degrees. So you can kind of tell that there is significantly less dissolved oxygen present at the 5 degree point, or at the 40 degree point, than at the 5 degree point, right? So if we think about this, right, our dissolved oxygen at 40 degrees Celsius, right, that we just calculated, was 0.212 millimolar, and at 5 degrees Celsius it was 0.403 millimolar. There's a lot of actual direct application to this. As the global temperature warms, right, the amount of dissolved oxygen in our water is going to start decreasing in terms of the ocean, which can cause issues for fish. Fish rely on dissolved oxygen in water to breathe. They're using gills to get their oxygen, not lungs, but those gills siphon out the dissolved oxygen dissolved in water. It's for this reason that generally, not always, but most big fish colonies are in cold water areas of the ocean, because those areas have much more dissolved oxygen present in the water. Kind of neat. If you have any questions, please let me know. Office hours, email, what have you.